If you think about it, there is a place for all kinds of things surrounding us where they can be showcased and celebrated. Galleries, exhibits, museums for automobiles, for playing cards, for cast iron stoves, for stuffed animals, for dishes, even for law enforcement. Wouldn't it be important, or even well overdue, to create such a place for something that has always fascinated humans and occupied us to no end? A gallery for light, and the people who throughout millennia have studied ways to decipher the essence of light. Let's begin with a virtual attempt. The first documented investigation of light took place in Greece in 500 BC. The scholar Empedocles assumed that things were visible because the eyes emitted rays. The mathematician Euclid elaborated on this theory and about 150 years later formulated his own theorem of intersecting lines. Objects appear smaller the further away they are. Euclid discovered the following phenomenon. If you spread two fingers before your eyes so that a distant object is held between the two fingers, as it were, then a mathematical equation results. The distance between the two fingers and the distance between the fingers and the eye has the exact same ratio as the size of the object and the distance from the object to the eye of the observer. This discovery was an important stage in the development of geometry and also for the Greek economy. Distances, that is, trade routes, could be calculated. The definition of length using measurements made by laser light has long since replaced the original meter as the standard quantity. Today, light plays a more important role than ever before in the measuring of distances. Using laser light, researchers can achieve precise measurements to less than 1/1000th of a meter. This means that a single millimeter can again be divided into 1,000,000 sections. A Muslim scholar explained the actual function of the human eye 1,500 years later. Alhazen realized that the eye does not emit any vision rays, but rather receives light. He defined the natural laws of light reflection. Angle of incidence equals angle of reflection. This principle has become common knowledge, but only the groundbreaking discoveries of Alhazen on diffuse light reflection explain why we see the things we see. Matte surfaces do not appear like a mirror because they reflect light in all directions. Without this effect, our environment would be a hall of mirrors. Reflection is the basic principle of fiberglass technology. The explosive growth of digital communication would not have been possible without this principle. A fiberglass cable allows an enormous quantity of data to be transmitted. A single glass fiber with the same diameter as a human hair could carry every telephone conversation in the world at the same time. Light makes this possible. It is the carrier of information. Digital data in the form of very short laser light signals race through an ultra-thin core fiber covered by lower refractive index glass. By the way, glass fibers also carry multiple kilowatt laser power for industrial material processing. Around 1200 AD, Alhazen's discoveries were translated into Latin. They inspired European scholars to research further. The Franciscan monk, Roger Bacon, worked intensely on the functioning of lenses. He is considered to be the inventor of eyeglasses. Though he was given the nickname Dr. Mirabilis, the amazing doctor, his scientific recognition was relatively small. In fact, his work brought him again and again into conflict with the church, and he spent many years in prison. The Protestant Isaac Newton is credited with discovering the spectral colors, the recognition that light is composed of different colors, and that white light comes from mixing all colors of light. This was a contradiction of the French philosopher and natural scientist René Descartes. He was Catholic and felt obliged to the Catholic Church's claim of absolute supremacy in answering questions about natural science. Newton was able to refute these claims with a simple experiment. Using a prism, he separated the light into its spectral colors, that is, into rays of varying color. Then he isolated the red color beam by guiding it through a hole in a board. Newton then guided this red beam again through a prism. If colorful light were mixed light, as Descartes asserted, then the beam would have had to split up again into various colors. But the beam stayed red. This was clear proof, and Descartes was impressively refuted. It was also a victory for the Enlightenment, and science had once again emancipated itself from the church and its claim to be the supreme authority in matters of natural science. But even Newton's ideas were still far away from what we know about light today. Like Descartes, he still believed that light consisted of particles. The Dutch physicist Christian Huygens believed that light was in fact a wave. He was a contemporary of Newton, and he was able to establish his wave theory in opposition to Newton's. But the proof took more than 100 years. In what is known as the double-slit experiment, the Englishman Thomas Young proved that light behaved like waves on the surface of water. It is bent in narrow slits and forms interference patterns. Long-wave light is red. Outside the visible range, we know this is infrared light. We feel it on our skin as heat, but this heat radiation can also be made visible. Using a thermal image camera, we can see minute thermal differences. As the light waves become shorter, the colors change, from red to orange, to blue to purple. And also here, light becomes invisible at a certain wavelength. Light with very short wavelengths include the ultraviolet rays and X-rays, which have an even shorter wavelength and are no longer considered light, just like the radioactive rays at the open end of the electromagnetic spectrum. At the blue end of the visible spectrum was one of the final unsolved mysteries of classical physics, the ultraviolet catastrophe. Max Planck solved it, ushering in a new era with the incidental quantizing of rays. Behind many an insignificant final mystery lies a whole new world. Albert Einstein seized on Planck's quantization to describe another unexplained phenomena of his time, the photoelectric effect. This is the ability of light to release electrons from an atom. Nonetheless, this does not depend on radiation intensity, but rather starts only with the specific color of the light. Only when the energy of a light quantum, which we call a photon today, is sufficient to knock out an electron is this electron actually released. In his explanation, Einstein again described light as a particle, thus contradicting the wave theory. Light would have to consist of a quanta with defined energy. Quite a provocative idea at the time, but it has been confirmed. Since then, we've been forced to live with the unimaginable idea that light, and any matter otherwise, possesses properties of particle as well as of wave. This wave-particle duality is still difficult to understand. But light presented other challenges, very concrete ones. Albert Einstein's father was the first to illuminate the Munich Oktoberfest with electricity in 1884. In his electronics store, he sold an invention that the American Thomas Alva Edison had made several years before. Edison developed the first functional light bulb at the same time as the Englishman Joseph Swan. Edison also invented, if you will, the lifestyle of the 20th century, the electrified world. Artificial light changed the face of the earth. In 1904, 1 year before Einstein declared the photoelectric effect, the conceptual forefathers of the motion picture died, the Frenchman Etienne Jules Marey and the American Edward Muybridge. Marey tried to solve the mystery of flight by photographing the sequence of a flying bird at intervals of a few milliseconds. It was then only a small step towards the camera which could provide motion pictures. With the invention of the film camera, the Lumiere brothers achieved this. A new art form was born, the light show, or film. Using visual technologies, we not only determine that we see something, but we determine what we see as well. During the 20th century, both life and technical progress accelerated. Charles Townes with the invention of the maser in 1954 and Theodore Maiman with the construction of the first laser 6 years later opened up a world of unexpected possibilities in the use of light. Many advanced technologies of the 21st century are customized properties of laser light. Communication and measurement technology, biotechnology, medical therapy, and last but not least, modern production technology. Contactless micro or nano manipulation, ultra-fast physics, quantum cryptography, and optical computers are the key words for the technological future. Laser technology is the foundation for all of them. No other phenomenon has fascinated humanity quite like light, and none has been developed into a tool to such extent. Many of light's secrets have been uncovered in the recent years, decades, and centuries, but many more puzzles remain to be solved. Discovery never ends, and new knowledge always means new questions. Is there really any such thing as a final secret?